Okay, hi everybody. We are going to continue our discussion yesterday on induction. I hope you enjoyed, for those of you that were here in the 10 minutes before lecture, I hope you enjoyed that video. They, again, pretty much did an entire crash course. I mean, I guess they do call it a crash course, they're in the title, but they did an entire crash course on induction generators and transformers, and they even mentioned Tesla coil in there, which we're building to. And they mentioned all of that in about 8.5 minutes, and you know, it's taken us all week to really build to this point. So when they say crash course, they really mean a crash course. That video was really fast, but hopefully after these lectures you can go back and you can maybe watch that video and you know, maybe make heads or tails of more details in it, because it really does make sense, and it's a really good summary of kind of the overarching themes. Okay, so before we move on to transformers, because we finished with generators yesterday, let's go back and do a little bit of a refresher from yesterday. So we'll do one of the problems that we skipped yesterday as to sort of allow our brains to sort of wake up a little bit. Okay, so here's a question. A conducting rod, oh, it's still highlighted, there we go. A conducting rod slides down between two frictionless vertical copper tracks. Now, I mean, in real life, how could it be frictionless? It can't be in real life. So I guess we just have to use our physics pretend brain that it is frictionless. And it slides down at a known speed that you can measure in real life of 4 meters per second. So the speed of the bar is, you know, being pulled down by gravity, and you can measure it at 4 meters per second. And it's falling inside of a perpendicular magnetic field of strength 0.5 Tesla. So the premise here is the conducting wire, or the conducting rod, is touching these rails, and at the top of it, a resistor connects the two rails. Now that resistor could be a battery, it could just be a carbon resistor, could be literally anything electrical that requires electrical energy to run. And this completes a loop. So this bar and rail completes, oops, loop does not have a T in it, completes a loop. So that's a conducting loop. That means current can flow through this loop. And because it's vertical, gravity obviously will pull on the bar, and because there's nothing holding up the bar will fall. So since this is in an external B field, as indicated in the picture, as the bar falls, we are changing how many field lines are going through the enclosed area. Right, as the bar falls, we are including more and more and more field lines. So that's going to be a Faraday law thing. You know, you're changing how much flux is going through an enclosed area. So that means you're going to get an induced voltage, and the induced voltage means you're going to get an induced current, because here we have a closed loop, and you know, the induced current is going to be an eddy current, right? It's going to resist the change. And produce a back EMF, and that's gonna provide an upward magnetic force on the bar. Just let me scroll up briefly to remind you what this is referring to. Remember, we watched this video yesterday with the eddy currents providing the backwards magnetic force, and it made this block of aluminum fall very slowly. We also sort of saw this notion in a video I showed you in our theme song on our physics page, and it's pretty much the same phenomenon that you get in a railgun as well. So that's just kind of building off of that idea there. So let's figure out, before we jump into this question mathematically, let's sort of figure it out conceptually. Okay, so the key here is that it's falling at a constant speed, which means it's hit terminal velocity. It means it's moving down fast enough that the magnetic force on ILB in the wire is directly combating the force of gravity. So the net acceleration is 0. F net equals 0. So let's conceptually kind of figure out what's going on. The speed of the bar is down, so we are increasing the number of field lines to the right through the rails. Now, Lenz's law says we want to oppose that change, the change being an increase in field lines to the right, so we want to decrease the field lines to the right. So the induced magnetic field will be in the other direction. This is going to be B induced. It's going to be in the opposite direction. So we use our right-hand rule, thumb in the direction of the induced B field, and your fingers, fingernails will curl in the direction of the induced current. So this tells me the induced current is going to be that way. Now, if we know there is a current in this rod traveling to the left, or perhaps out of the page, depending on your perspective, we can use our right-hand rule and we can figure out what kind of magnetic force this length of wire or rod will feel as a result of that external B field. So right-hand rule, again, you can use the physics gangster sign if you want. You can use the give me money right-hand rule, whichever one floats your boat. I'm going to use a give me money one. So right hand, fingernails in the direction of magnetic field. So my fingernails are pointing to the right. My thumb is pointing out of the board because that's the way the induced current is going. And the palm of my hand is facing up. And you can get the same conclusion if you use the physics gangster sign right-hand rule as well. So we know here that there's going to be a magnetic force upwards, and obviously gravity is pulling down. So the fact that this is known and empirically seen to be traveling at a constant speed of 4 meters per second, that means that the magnetic force is directly canceling out perfectly the gravitational force. So whatever its speed it's traveling at, it's going to be constant because the acceleration is 0. Now, notice here how they want the electrical energy dissipated in the resistor. Now, there's 2 ways to do this. Let's do it the way I think the question expects. There's an actual much easier way to do this, but it's sort of a trick. So as with before, I keep saying it almost doesn't matter what the question's asking. The underlying concepts are what governs how you start the question. So ultimately, this is a forces problem coupled with, well, we're going to talk about coupled circuits, I guess, later. So I guess no pun intended, but coupled with, it's a forces question coupled with Faraday's law. So let's start with forces. So we know the magnetic force is up. We know the gravitational force is down. We know F net equals ma, and that because it's at a constant speed, the acceleration is equal to 0. All right, now let's start expanding this because new question, everything's new, everything's confusing. So let's just stick to basics. Let's keep our head on our shoulders and use our critical thinking and problem solving skills. So we have the net force is going to be the magnetic force minus gravity, and that's going to equal 0. And this is going to be, what's the magnetic force in this case? Well, it's not the force on an individually charged particle. It's the magnetic force on a length of wire. So it's I, L, and then B. Do we know anything about, well, we don't know I, we can figure out I. Do we know anything about the length? Let's just read back here, because I need to know what I need to swap out and what I don't need to swap out. So it looks like the length we know, the magnetic field we know, the current in the wire is something that is obviously induced through Faraday's law, so we'll have to tackle that momentarily. Gravity we know. Mass. Do we know mass? The resistance. We don't need resistance yet. The rod maintains electrical contact. We have resistance. attached between the tops of the track, find the electrical energy. So we don't know mass. So I'm going to have to trust that mass will cancel in some fashion. So for now, I'm just going to leave it. However, I know, because from context in the problem, I know I can get I from Faraday's law coupled with Ohm's law. We've done lots of examples where we first calculate induced EMF or voltage, induced voltage, and then we use that in Ohm's law. So let's do that now. So we start with something we know, right? Free body diagram, F net equals MA. That analysis helped guide us to Faraday's law to swap out one of our unknowns. So Faraday's law says the induced EMF equals the derivative of the flux with respect to time. And the flux in this case is going to be BA. Now, I guess it's BA cos theta, but the question says that the B field is perpendicular to the loop. So the vector A is also perpendicular to the loop. So the vector A and the B field are actually parallel. So theta equals 0 and cos of 0 is 1. So here's our derivative. So we ask ourselves, what's changing? Is the strength of the B field changing? No. So we can actually factor that out of the derivative and then say, okay, well, A is changing. Yes, it is. As time goes on, the area is getting bigger. Now, what kind of area is this? Is this a circle that's just the radius is getting bigger or smaller with time? Is this a square where the side length is getting bigger with time? Close. We have a rectangle, and the width of the rectangle, well, I guess maybe I'll just draw it over here. The width of the rectangle is fixed, or I guess that they call that the length of the rod, I suppose. They call that L. However, but the height of the rectangle is constantly getting bigger. And the height, or well, you could say the height is a function of speed, v times t. So here, when you plug this into the equation, you're going to get the derivative of v times t with respect to t. And what's the derivative of v times t with respect to t? Well, velocity is a constant. So it's just literally one of the easiest derivatives you could possibly do. The derivative of a constant times t is just the constant. So this is going to be bv. Okay, so that's the EMF, B times V. Now here, sorry, I missed a variable. I totally missed a variable. This is, sorry, this is height. This is height, but I was missing length. There we go. There we go. Sorry, I was missing a variable there. I got overexcited. So yeah, the derivative of area with respect to time. Area is length times width, or I guess in this case, length times height. So length is a constant, so you can factor length out of the derivative, so BL, and then the derivative of VT with respect to time is just V. Or you can actually even just factor out V, because V is also a constant. So the derivative of T with respect to T is 1. So however you want to think of the math, it's the same thing. So VBL, there you go, there's your equation, and that's the induced voltage. Now, because we've already done the first part of our analysis, we know we want current. We know that that's the desired thing. So current can be found with Ohm's law. Voltage equals current times resistance, which says current is going to be VBL divided by R. Okay. And plugging this in, I'm going to get VBL divided by R times LB equals mg. Okay, so I think I have everything except m. in this case. Let me just write one more to simplify some things. VBL squared B squared over R G equals M. So I think I've got V, I've got B, I've got L, I've got R, and I've got G. So there, I can solve for M. Okay, I didn't know I needed to solve for M. So let's see why. Why do I need M? Why is M the only thing listed here? What am I actually asking for? Or what are they asking for? Find the electrical energy dissipated in the resistor in 0.2 seconds, so in some amount of time. So here is actually where the analysis sort of diverges. You can do this two ways. Electrical energy, you know, is going to be power times time. And we know power can be represented in a few ways, but V squared over R is probably the safest way to go about solving for power, and you can multiply this by time. So you could say, you know, the voltage, we know, B squared V squared L squared over R times delta T, right? And then there you go. So it turns out we didn't even need M. Now, interestingly, I've said this before, I alluded to the fact I really wanted you to dig deep with these concepts. There's no such thing as a free lunch, okay? What is the source of the current? You could say it's Faraday's law, you could say it's the voltage that's induced, yes, you would be right. But what's causing Faraday's law to kick in? Okay, if it weren't for blank, Faraday's law wouldn't kick in. And the answer is gravity. Okay, it's gravity is the force responsible for pulling this rod down, which is what is changing the area, which is what's inducing the voltage through Faraday's law, which is what's causing the current. Right? So ultimately, the energy that is dissipated, again, conservation of energy is a very, very beautiful and elegant idea because it skips all the details. It skips all the middlemen. Energy says whatever energy you put in, you have to get out. Okay, so what energy, the other way we can analyze this is say E total equals E total prime. Whatever energy we've put in, whatever work we've done on the system is whatever energy is in the system. So what energy did we put in the system? Well, the work done on the system is actually going to be the change in the gravitational potential energy. This rod, as it's falling, is using some of its gravitational potential energy and converting it not into kinetic energy because it's a constant 4 meters per second. So that loss in gravitational energy is not going to speeding up the object as it normally would if you were to drop an object. Instead, that energy is being transformed and flows, so to speak, into electrical energy. So this is going to equal the electrical energy. So here, what you can actually say is that the electrical energy that we're looking for in the question is going to be given by mg delta H. So the change in gravitational energy over this time frame is going to give you the amount of energy dissipated in the circuit during this time frame. And I think that's just amazing because this really, really, really truly illustrates how Faraday's law serves as the mechanism that converts mechanical energy into electrical energy. This equation right here, it's just so beautiful, I think, so beautiful. So M, we know what M is. M is VB squared L squared over RG, that's M. G, and delta H. Delta H is the height that this object falls, or this rod falls, over the time. Now it's moving at a constant speed, so this is just a kinematics problem. Here, the height that it falls is simply going to be velocity times time, or I should really say delta T. So this here is going to be the height that the rod falls. And then when you simplify everything, you're going to get V squared B squared L squared over RG delta T. And that is actually the same equation. Oh, maybe I should draw that in a different color. That is actually the same equation we obtained by setting up a completely different formula. We set up, you know, before we set up the energy equals power times time, where the power was V squared over R. Completely different than mg delta H, but the two produce exactly the same result. And this really is the beautiful part of physics. It really is. It's that the math behind the physics really does provide insight into the underlying concepts that are happening here. So I think this question is super cool. And for the record, I got this question from a past test, not one of my tests, a test from a different instructor for this class. And you know, I think this is a fairly involved question. I think there's a lot of themes that are going on in this question, and that you know, I think this is a pretty challenging question overall. So you know, something to consider. You know, if you're wanting to gauge this class over the summer compared to other iterations, you know, this is an example of what they would have found on their midterm. And you know, you obviously know your own midterm, so something to compare against. Okay, so this one here, we don't have time to do it, but I've included the solution here for you to review. So please go back and do that. Okay, so we reviewed generators yesterday and how cars, we talked about the alternator in a car, which is effectively a generator in a car, and how way back in the 1920s, you had to crank a car by hand. Now we use a battery, and you know, that conversation sort of digressed into explaining why I drive a standard instead of an automatic. And we also briefly talked about an electric car, like a Tesla, for instance, and how there is no engine in a car. It's a DC motor in the wheels, and the DC motor in the wheels can then switch from being a DC motor to being a generator to charge the battery when you brake. So it's all really cool, and it all hinges on Faraday's law. Whether you have a gasoline engine or an electric car, Faraday's law is forever crucial in cars. Okay, so the last chapter we're going to talk about in electricity and magnetism is transformers. And transformers is really the crown jewels, so to speak, of Physics 137. In Physics 136, we spent all semester building up to angular momentum. And angular momentum is, I think, absolutely gorgeous. It's downright beautiful. It really explains pretty much every classical phenomenon that we experience. You know, it explains lots of things, celestial things like the orbits. Yes, you need some calculus and some more advanced stuff, but the root of it is really conservation of angular momentum. It explains why planets travel faster when they're at a smaller radius compared to a longer radius, which explains Kepler's laws, which you may have learned in high school. And it explains why the Earth precesses. It explains why a spinning top precesses. It's so cool. It explains why angular momentum explains why bikes work and you don't fall over when you ride a bike. It's so incredibly cool. And it took all semester for us to build to angular momentum, and that's us now with transformers. We needed everything. We need to know knowledge about charge. We needed to know knowledge about circuits and electricity. Then we needed to know Ampere's law. Then we needed to know Faraday's law. And then now we need to know about a transformer. And then we can really understand what a Tesla coil is doing. So I just think it's so cool. So I hope you appreciate this last little chapter here. So what is a transformer? So we obviously have to explain to you what a transformer is in order to talk about it. So consider this for a second. Okay, so we have one coil that is powered with some sort of current. It could be with a battery, it could be an AC current in a wall, okay, whatever. Let's just say we have a coil, and we've already established with Ampere's law that the B field due to a coil is going to look very similar to that of a bar magnet. So that's where the electric field or the magnetic field lines here resemble, right? They look like the B field lines due to a bar magnet. Okay, great. That's old news. Old news. So if we bring in a second coil. Now this second coil is not, it could be part of a circuit, but the second coil is not hooked up to a power source. Okay, now, I mean, again, it could be hooked up to a complete circuit, but that circuit itself won't necessarily have a battery. I mean, it might have a battery, but you know, to illustrate my point, let's assume it does not have a battery. Okay, well, if you bring the second coil nearby, like physically in close proximity to the first coil, then you can see that the magnetic field lines will eventually pass through the second coil. All right. Now, that's all fine and dandy, okay? But remember, a steady magnetic field will not induce a current because Faraday's law says you have to have a changing flux. So, you know, maybe the process in which you move the coil in, yes, there will be a brief change in flux. That is true. However, once the coil has been moved into position and then remains stationary, then the B field lines from that coil will be steady because the current in that other coil is, let's assume DC for a second and steady. Then there will be, let's say 6, 7, 10, whatever number of field lines through the second coil, and it'll be stagnant. It won't be changing. So if that second coil is brought in and then remains stationary, nothing will happen. I mean, there might be a little blip as you're moving it into position, but once it's there, nothing will happen. If the original coil's current were to change, then the B field felt by the second coil would change. So this is really saying, okay, well, if the primary coil, or the coil that is actually hooked up to a battery, if it's hooked up to a DC battery, like a 9-volt or a AA, then it's a steady current and steady B field. However, if you hook up that coil, that same coil, to not a battery, but let's say your wall outlet, something that has an alternating current source. So forward, back, forward, back, forward, back, in a very similar fashion to how I described an induction cooktop needing to be AC current. Then the B fields felt by the secondary coil will be constantly changing direction. Perhaps same magnitude, but always changing direction. So this would actually result in a changing, or I should say a constantly changing flux. So the key here is, for a transformer, you need to have AC current in the primary coil, because you need to have the constantly changing flux. Now, I remember one year I taught this class, someone raised their hand and said, well, Mark, can't you just have a battery hooked up and you just keep switching the terminals of the battery? Wouldn't that work? And I'm like, okay, yeah, technically you're right. But if you want to sit there forever, flipping the battery back and forth, the ends of the terminals of the battery, in a very regular interval for, all day, every day till the battery dies, then go knock yourself out, go nuts. That job is probably the most menial job that exists on the face of the earth. So that is not something we want to do when we can automate that very easily using AC current. So anyway, in the event you have AC current, then you will definitely have an induced current in coil number 2. So this is really the premise of what a transformer is. So let's go through the math a little bit. Now the math isn't complicated, despite how the slide might look momentarily. That shouldn't be a P, that should be a B. Oh, let me change that to red so you can see it better. Oh, no, that should be a P, primary. Okay, sorry. So here, let's go through this for a second. So the primary coil meaning the one that is hooked up to electricity, would be able to produce a maximum changing flux of the second coil of d flux primary by dt. That's saying the flux, sorry, let me scroll back here so you can see. That's saying if you keep increasing the current and decreasing the current here, switching directions, that these field lines will keep switching back and forth. But not only does that cause a change in field in that coil, obviously this coil itself will feel a change in flux. So that's what this is saying here. It's saying the primary coil will be able to produce a maximum flux in the second coil equal to the maximum flux that it feels. You can't say, oh, if I myself have 10 field lines going through it, then you can't possibly have more than 10 field lines going through it. I'm only making 10 field lines. So it's saying at most, if I have 10 field lines, at most, you have 10 field lines. You might have less than 10 field lines because you might be kind of farther away, but at most you have 10 field lines. So logically, that's what this is saying. It's saying that the change in flux of the primary is bigger than, this really should say or equal to the change in flux in the secondary. Now, the question is, how do we maximize this? You know, obviously, if the primary itself is experiencing, let's say, 10 field lines, then it's impossible to make the secondary feel something more than 10, right? Because the primary is only generating, say, 10 field lines. But obviously, Faraday's law is the change in flux. So we want to maximize the amount of flux, the changing flux, that the secondary coil feels. So if the secondary coil is a little bit far away, then it might only be feeling 5 of the 10 field lines already. And then, you know, with the AC current, the field lines keep going from, you know, up to down, up to down, up to down. But then the changing flux in the secondary would only be 5 field lines that are changing, not 10 field lines that are changing. So the question really is, how do we maximize this? You know, we want it to be more efficient. If the primary has 10 changing field lines, we want to see, is there a way to make all 10 of those field lines also be felt by the secondary? Because we want to maximize our chances. This is what a transformer is. So here's the premise. You have a primary voltage source, and it really has to be, well, even if it's DC for a second, AC, DC, let's just assume it's just some sort of voltage source for a second. So there's going to be a current traveling in this wire, or in this coil, and then it comes back down this way. Now, using your right-hand rule, you can figure out the direction of the B field lines, or, well, actually, given the B field lines here, I drew the current in the wrong direction. I think it would have to be, let's see here, behind this way. There we go. So here, if you fingernails in the direction of the current, wrap them around the coil, your thumb points in the direction of the magnetic field. So the field that this current produces is as indicated in pink on the slide here. Now, without the iron core, and really what you're looking at here is you're looking at an iron core. It's literally just like a rectangular piece of iron. Without the iron core, then your loop, or your coil, would produce a magnetic field that looked like a bar magnet. Okay, without the iron core. With the iron core, because iron is the way, iron's magnetic, or ferromagnetic, I guess is what they call it. It can iron, and most metals, but iron specifically, has the ability to sort of channel the magnetic field. It's a way in which we can manipulate, it's like a road for the magnetic field. So what we have here is if, and this is an artificial thing that physicists had to think about and impose, and we could say if we could use an iron core to channel 100% or close to 100% of the B field generated by the primary coil, we can funnel it like a lazy river around in a circle, or I guess in a square, around the iron core. And this minimizes waste. This focuses the magnetic field into a well-defined loop, and iron is ferromagnetic, so the magnetic field wants to travel through that path. And then the reason why this is helpful is because now we have a very concrete, reliable, robust, dependable way to have the magnetic field generated by the primary get funneled through. So let me draw an arrow here. I'll say the iron core, the iron core funnels the magnetic field from primary through, don't buy a Windows machine, primary through, through the secondary. So really what we've done here is we've turned that inequality. We knew that, like, if the primary generated 10 field lines, then the field lines felt by the secondary is less than or equal to 10, right? You obviously can't feel more field lines than what's produced. So really what we've done here is it's physicists it's a physicist thinking in advance. We want to maximize the number of field lines that go through the secondary. How can we do that? We can do that by creating a pathway, a road, a magnetic road for them to go through. And what we've done is we've changed that inequality into an equality. So this is the basis of how transformers work. The basis of how a transformer works is that the flux felt by the primary coil is the same as the flux felt by the secondary coil. That's the premise. Now, please understand, there is nothing in the laws of physics that says the flux felt by a secondary coil must always be equal to the flux felt by the primary. Clearly, I could turn on a coil here at my house, and you could just have a random coil sitting somewhere at your house. So that doesn't mean it's going to feel the presence of my coil, right? Just because there's a primary and a secondary somewhere else in space does not necessarily mean the flux felt by the secondary in any way will be felt. So this equality here is not a law of nature. It is artificial and obtained by design. By design with the iron core. Okay. Okay, so that's the premise. Okay, so where does that leave us? Okay, now that we know the flux felt by the secondary is able to be forced to be equal to the flux felt by the primary. Now, and I've already sort of spoiled my story here, we need AC current. Here's why. Let's assume we had DC current. Well, if we had DC current, then the field lines generated by the primary would be constant. Okay, now if the field lines if the field lines from the primary are constant, then they're going to be constant traveling through the secondary. And if they're constant traveling through the secondary, then the change in flux through the secondary will equal 0. The flux itself is non-zero, that's true, because there are field lines going through the secondary. But the change in flux, the change in the number of field lines going through the secondary will be 0, because if it's 3, then it's always 3. If it's 10, then it's always 10. So DC means one direction. There's a lot of music references in here. AC/DC, that's a rock band. One Direction is a rock band, or not a rock band, I don't know, what do you call them? A boy band, a pop band? I don't know. A musical group. Lots of, and then AC or DC or Marvel. Lots of little funny physics jokes here. Anyway, point being, you can't get a changing flux with a DC current. You can get a non-zero flux, but it's constant. So there's the problem. In order to get a changing flux, you would need to constantly increase the source of the DC current. You'd need to, constantly be adding more batteries, which would produce a larger current, which would produce a changing flux. But that's not sustainable. You can't just keep adding batteries forever. So here comes AC current. Now, AC current has a bit of a tumultuous past. It's a kind of a funny story, actually. Edison is largely considered to be the father of DC current. Now, Edison, people call Edison all sorts of things. They say, he was a physicist or an inventor or something along those lines. Yeah, he dabbled in that, but above all else, Edison was a businessman. Okay, he was largely viewed as a business guy, and as a business guy, yes, he had ideas for his business to make money and to monopolize and stuff like that. Well, monopolize even kind of looks like the man on the Monopoly board, but anyway, he was a businessman above all else, and he held the patent for DC current. So what happens is, often the case with business and science, and we're seeing this now with the global, with like carbon tax and global warming and fossil fuels, business and science don't mix. There's too much money to be made in oil. So politics says, screw the environment, we're going to continue burning oil. Same thing sort of happened with Edison, just with less environmental impacts. He had a lot of money invested in DC current because it was his patent. So he used his marketing skills and his business power, and he really, really forced the market to accept DC current. And it was actually very unsafe. Edison, at first, when electricity was first delivered to the home, it was actually delivered via DC current. And it was very unsafe because with DC current, you couldn't generate a high voltage. It was a safe, well, quote unquote, safe voltage. It was a lower voltage, a couple hundred volts, kind of like what we have now in our house. The problem with that is when you drop the voltage, you increase the current. So, sparks weren't happening because it was a low voltage and and didn't reach the breakdown voltage of very many items. But the problem was, if two wires ever got crossed, or if there was ever a short in the circuit, or if you were screwing in a light bulb and your finger slipped and your finger touched the terminals, there would be a very high current that is experienced when you touch those things. And as we mentioned earlier, voltage does not kill you, it's current that kills you. It's how much charge will pass through your body. It's not the height at which the charge falls, it's how much charge goes through your body. So DC current it proved to be quite dangerous, actually. And eventually AC current took over despite Edison's push for DC current, because it proved to be so unsafe. So anyway, I digress. Physics is really interesting. If you actually look at the history of physics in the early 1900s, it's really interesting to look at kind of how science and business don't mix, and how the fundamental principles of physics actually eventually won because you could use physics to be safer in delivering the same service. So anyway, I just think that's really cool. Back to my point though. Okay, so aside from safety, maybe what's a more economic reason, money-wise? Everything's about money. What's a more economic reason for not using DC current? Well, as was mentioned in the video that I showed ahead of time, which you can always go back and look at later, let's look at power loss, how the expense involved in delivering electricity to the home. So we know power, well, power equals IV, right? Another way we can talk about power is we could rearrange this and say I squared R. So why do I use it this way? Well, current in the wire is constant everywhere in the wire, so that's easy. The resistance of the wire you can measure, resistivity times length divided by cross-sectional area. So you can measure the resistance. And power, well, power is fixed. Okay, whatever power the power plant can generate is a fixed value, and that's not up for debate. So this is a fixed value. The resistance is a fixed value. So in order to get a decent amount of power to the household, and you need a lot of power in the household. I mean, you've got stoves and lights and air conditioners and washing machines and dryers, and they could all be working simultaneously. You need a lot of power to be delivered to an individual household, let alone power being generated from a power station in order to sustain an entire city's worth of power consumption, right? So this equation says the only way to obtain, maybe in a different color, the only way to obtain high power is high current. Okay, but current, we know, causes heat loss. The more current you have, let's say an incandescent light bulb. In fact, this is the exact premise of an incandescent light bulb. You push so much current through such a small wire that you're actually taking advantage of the heat loss, because it's the heat generated that makes the wire glow. And we use the light from the glowing wire as a light bulb. That's what an incandescent light bulb is. I mean, at the time, I think that was a genius idea. Don't get me wrong. It was a genius idea. But in terms of delivering power from a single power station over power lines to the entire city, it's not like these are necessarily glowing, but these wires are going to be pretty hot, and they're going to be just pumping out a lot of heat into the atmosphere. And thus be very expensive, because you're going to be losing a lot of electrical energy in the form of heat just before it even reaches your house. Now, Nikola Tesla came along in and around the early 1900s, and he proposed AC current. Now, Nikola Tesla actually died, I believe, before AC current was adopted as just standard use. And that's a shame that he never got to live to see that he was actually correct. But after he passed, yes, society finally said, okay, yeah, this is ridiculous. Let's just switch to AC. It's just cheaper and safer. But what Tesla was trying to explain is that the power output from the electricity plant is fixed. Okay, so what kind of power output do you get from a power plant? Well, we know power is IV. Okay, now if we can get a really, really, really high voltage, then the current leaving the power plant can be very small. Okay, because normally you say, well, if you increase voltage, you're going to increase the power. Well, if the power output is fixed, you can only increase, P equals IV, right? You think, oh, Mark, if you increase voltage, you're going to increase power. Well, only if the power source is able to keep up. There's no such thing as an infinite power, right? So if the power generated from a power plant inherently has a maximum, which it does, then if you continue to amp up the voltage, then something's got to give, and what's going to give is the current. So if there is a constant on the left-hand side, then as voltage goes up, current goes down. Kind of like PV equals nRT. If PV is a constant, then as pressure goes up, volume goes down, right? As you increase the pressure of a certain volume of gas, and then the volume of gas will go down. That's how you compress gas, obviously. So that's kind of what's happening here. Now, why is this useful? Well, if you look at the power loss in the wires as it's being delivered to your house, then that's going to be given by I squared times R. So if there's a way in which you can manipulate the current to be super low, then, and only then, can you minimize how much heat you lose due to current delivering to the houses. So that's pretty much what this is saying here. It's saying what comes out of the plant is a constant value. So if you waste less, then more will get to your house. Okay? That's what Tesla was trying to say. And Edison was very powerful, I guess, a very powerful businessman at the time, because electricity was new. I mean, like, electricity in households before the 1900s was like far and few in between. So, you know, the mass production of electricity in the households was like in and around the turn of the century. And Edison was largely the person responsible in North America for this shift. So he had incredible wealth, incredible influence, and incredible power. And it was all about money for him. So, you know, even a logical argument like Tesla's had, it just didn't carry any weight until much, much, much later. Okay, so here's an example from your textbook, or at least the recommended textbook. So example 21-11, so chapter 21, I guess example 11. So the transmission lines. So an average of 120 kilowatts, watts being power, kilowatts of electric power is sent to a small town from a power plant that is 10 kilometers away. The transmission lines have a total resistance of something very small, okay? So the resistance is 0.4 ohms. Calculate the power loss if the power is transmitted at 240 volts versus 24,000 volts. Okay, so you might be wondering, well, Mark, there's a few different equations for power, right? There's P equals IV, P equals I squared R, P equals, you know, V squared over R. So here, we cannot use V squared over R because R is the resistance of the transmission lines. We don't know what the voltage drop along the transmission lines will be, okay? We know what the voltage is coming out of the power plant, right? It's assumed to be 240 volts. But we don't know what the voltage drop, right? You know, if we want to, don't forget, if we had like a battery here with a resistor, and we want to know, let's say we want to know the power, through, or the power of the resistor, you need the voltage drop across the resistor. We know the voltage of the power plant, it's presumed to be 240 volts, but we don't know what the voltage drop across the power lines are going to be, because the power lines are only one step in the process, right? The power lines are then, they go to your house uses more voltage, so I suppose I should draw this a little bit better. I suppose I should say there's a lot of resistors here from your house. Okay, so we don't know, there's more than one voltage drop along the way, so we don't know what the voltage drop of specifically the power lines will be. So, you know, if we did know that, then yes, we could use this equation, but there's no guaranteed way to know what the voltage drop across the power lines will be. So we're not able to use this because we don't know the voltage drop specifically of the power lines. The given voltages are applied across the lines, yeah, plus the load being the town or the house. However, the town or the house is in series with the power line, obviously. So what we do know is we know the current in the power lines will be the same as the current that's delivered to the town. So that is something that we can dependably know. And also that's something we could just measure, but it's constant everywhere in the circuit. So we can say the power loss in the wire is going to be a rearrangement of P equals V squared over R. It's going to be P equals I squared R. So for both cases, you see here that the voltage of the power source, well, okay, so here we say, here, if for A, well, let me change color here. So for A, if the voltage of the, what is it, the power plant? So we'll say the plant is 240 volts, then what will the current be? Well, the current will be P divided by V. What is the average electrical power of the power plant is 120 kilowatts, and it's being delivered at 240 volts. So this is going to be half times 10 to the 3, 0.5 times 10 to the 3, which is going to be 500 amps. For B, if the voltage of the plant equals 24 times 10 to the 3 volts, 24,000 volts, then the current is going to equal P over V, is going to be 120 times 10 to the 3 watts divided by, I should say volts there if I'm going to say watts there, divided by 24 times 10 to the 3 watts, not watts, volts. And this is going to be 24 divided by 120, 5, I guess. Roughly 5 amps. So we've got different currents in case 1 and case 2. So the power loss is going to equal I squared times R. Now in both cases, case 1 and case 2, it's got the same resistance, right? The voltage at which the power plant delivers the current is not a function or in no way impacting the resistance of the power lines. So both cases R is the same. So the power loss in the first case is going to be 500 squared times 0.4 ohms, right? That was resistance, yep. And in this case, it's going to be 5 squared times 0.4 ohms. Now, this is going to be what? 5 squared times 100 squared times 0.4. And this is simply just going to be 5 squared times 0.4. So you see here now, I mean, if you want to know the actual number, it's going to be 100 kilowatts versus, what was the other one? 10 watts. Now, that's if you had a calculator. I don't really like using calculators, so I like to factor and cancel. So here I can say, look at the ratio. Well, if you divide these two numbers, the only difference is 100 squared, which is going to be 10 to the 4, which is, I believe, 10,000 times. So by upping the voltage to 24,000 volts, you're actually saving 10,000 times as much energy. You're able to get 10,000 times as much energy delivered to your household by upping the voltage. Now, what's the difference in voltage? Well, what is it? 24 volts to 24,000 volts? No, to 240. So let me in a different color here. I'll say, however, voltage 2 divided by voltage 1, it's going to be 24,000 divided by 240. So that's going to be, 100, I think. So 100 times increase of volts produces 10,000 times the savings of energy. And that's what Tesla was trying to say. Tesla was trying to say, look, we're doing this all wrong. not only is DC current extremely dangerous because you're transmitting the voltage, you're transmitting the current at a very low voltage, which makes it a very high current. Not only is that very wasteful in like electrically speaking, it's also very dangerous because you have such a high current. So like Tesla was just really frustrated that you know he wasn't being listened to. So this is really this is Tesla's crowning achievement, was he was really pushing the transformer. He was saying like, look, we can boost the voltage coming out of the power plant. We can send the electricity through the power lines at 24,000 volts or even higher at times. And we can have super efficient power transmission, super efficient. And we can use a transformer at the other end because it's AC current anyway. Well, at least what Tesla was proposing was AC current. You can use a transformer at the other end to bring it back down to a safe level. And then that way it's only going into the house. Like there isn't a long distance between the transformer and the house for it to lose energy, right? Most of the 10 kilometers that it travels is going to be very efficiently transmitted. So this is why AC current was being pushed for, because Tesla said, look, you can use a transformer to step up the voltage, you can use a transformer to step down the voltage on the other end and achieve a really efficient transmission of power. But it needed to be AC because two reasons. Transformers only work with AC current, and two, AC current is much safer than DC current. So let's look back to the math. Back to the math for a second. We do know that physicists are able to produce perfect transmission. And again, this is artificial. There's no way, there's no fundamental law of nature that says these two have to be equal to each other, right? We force this to be equal to each other using a proper engineering and design of a transformer with that iron core. Okay, now let's go a step further. What is flux? Well, we know flux is, well, if we only have one loop, then it's just this. But if you have multiple loops, then you multiply it by n, the number of turns in the primary. So we know the flux is the same. So, and we know Faraday's law. Faraday's law is that the induced EMF equals the number of turns in the primary times the flux, or the change in flux. So we know the change in flux is the same, but that does not mean the voltages that are induced will be the same. It just means the change in flux will be the same. So what we do here is we just take this equality, plug it into this equation, and then you simplify, and then you get something like this. So what I'm doing here is I'm saying V primary over NP equals D flux primary over DT, and then I'm saying VS over NS equals D flux secondary over DT, and we know that these two things are, oh, that's a terrible arrow sign. We know that these two things are equal to each other by design. Again, not a rule of nature. By design, we're confident in our engineering that that iron core is dependably making this B field felt equally in both coils. So then we can also equate this side. So then we end up getting voltage primary over N primary equals voltage secondary over N secondary. And that's where that equation comes from. Now, that's fine and dandy. We've derived an equation. This is called, well, colloquially, this is called the transformer equation. Let's think of the implications of this. Okay, let's rearrange this equation for the voltage of the secondary. Okay, so we just, you know, what math teachers, and this irks me to no end, when math teachers say cross multiply, okay, there is no such thing as cross multiply. That's not a mathematical operation. But anyway, if we isolate a very simple equation, for Vs, then we can actually look at what factors go into solving for the induced voltage in the secondary coil. And what's happening here is you see that the voltage in the secondary coil is going to be equal to the voltage in the primary coil multiplied by what we call the loop ratio. The loop ratio being Ns divided by Np, the number of loops in the secondary divided by the number of loops in the primary. So what this is saying is, if there are more turns or more loops in the secondary compared to the primary, that the induced voltage in the secondary will be larger than Vp, because that loop ratio is larger than 1. So let's say for instance you had 6,000 loops in the secondary, and you only had 6 loops in the primary. Then the loop ratio or the induced EMF in the secondary is actually going to be 1,000 times larger, which is actually like phenomenal. If we have about 120 volts coming in from our wall outlet. So if you hooked up your wall outlet to a piece of wire, and you had 6 loops in that piece of wire, and then you sort of had a nearby coil that had 1,000 turns in it, then that means the voltage induced in the second loop, or not 1,000, say 6,000 turns in it, then the voltage in that second loop is going to be 1,000 times larger. Instead of 120 volts, it's going to be 120,000 volts. Okay, that's a huge amount of extra voltage. And this is actually the premise of a Tesla coil. I'm going to zoom in here as best as I can. As best as I can. What's happening here with the Tesla coil is you have a primary coil at the base, and the primary coil only has a few turns. It only has 4 or 5, maybe 6 turns, okay? But this here is not actually a cylinder. What that is very, very, very thin copper wire. And it is wound so tightly and so precisely, and the gauge of the wire is so small that when you actually look at it, it's really hard to tell that they're made from individual loops. But it's individual wire that has been wound onto some sort of cylinder, whether it be a plastic cylinder or an iron cylinder, whatever. And it is wound so precisely that it looks like a cylinder instead of a coil. But it is, in fact, a coil with very thin wire. Now, the reason why it can be thin is because it carries less current. The primary wire is usually thicker because lower voltage, higher current. But conservation of energy, if you up the voltage, you have to down the current, because you can't just get more energy out of nowhere. So there's actually a very, very small amount of current in these wires. So you're allowed to get away with a very, very small gauge of wire, because the voltage that you're talking about is thousands of times larger than the wall outlet. So it's a very, very small amount of current. Now, here you see a man standing in a Faraday cage. So he's safe from the electrical shocks. Weirdly enough, they actually put the Tesla coil itself into a Faraday cage, which I thought was kind of fun. That just protects the circuitry in the Tesla coil if it decides to arc to the Tesla coil. Now, as with any good physicist, I have been right stupid a few times, and fool me once, shame on you. Fool me twice, shame on me. It's not even fool me twice. I think I've been shocked. We have a Tesla coil at school at UTM, and usually in this lecture, I would bring it in and I would demonstrate this exact thing for students. But unfortunately, I don't have one at my house. As much as I really really, really want one in my own house. I just don't. So anyway, I can't bring it in for you, but I have a cool video to show you a little bit later. But I've been shocked by the Tesla coil a few times, and as much as it hurts, like, you know, like when you shock yourself getting out of the seat of your car, you can get that little spark. It hurts, but it doesn't kill you, okay? Because it's a very low current. So I've been shocked by the Tesla coil a few times, and it you know, it jolts me, like I panic and drop whatever I'm holding, but by no means is it like, you know, a little bit of a shock and you're dead. Now, if you stood there grabbing it, continuously being shocked, yeah, that could probably do some damage. But you know, a very brief arcing to you probably won't hurt you, because the voltage is so high, the current is so low. Now, not only have I shocked myself with this more than once, which again was my fault. Gideon even told me, Mark, be careful, and then I shocked myself, and then he's like, aha, see, I told you, be careful. And then literally immediately after saying that sentence, he shocked himself. So, you know, it goes to show you that you can even know the physics and know what you do to need to be safe, but you know, sometimes the captivating nature of what you're looking at just makes logic go out the window. And then it gets even funnier. There was another physics prof at UTM, Joshua Milstein. He's one of the most hilarious people I've ever met. Super smart, really good physics prof. And right when our Tesla coil was brand new, he happened to be in the labs one day for something, and Gideon and I are like, hey Josh, come look at our Tesla coil. And we had learned from our mistakes. Gideon and I had learned from our mistakes. So for safety, we had put like a retort stand near the Tesla coil. So what we did for safety, because we didn't want to hurt ourselves or anyone else anymore, what we did was we effectively put a metal pole between us and the Tesla coil, which means the lightning would always arc to the retort stand or arc to the metal pole. It's effectively a lightning rod. And that was supposed to help protect us, you know, in case we did something stupid. And we told Josh, you know, hey Josh, you know, Mark has shocked himself a few times, Gideon shocked himself a few times, just be careful, you know, obviously stay away from the rod. And Josh is like, oh, I wonder what happens if you move the rod closer. And he reached out with his shoe to push the rod closer with his rubber shoe, and he got shocked in his foot through his shoe. And he's like, ow, that kind of hurt. So even Josh shocked himself, which I thought was kind of funny. And I remember Josh saying like, oh, I thought I would be safe because I had a rubber shoe. And I said, you know, that's a common fallacy. You know, if lightning or electricity has enough voltage to jump through, you know, a meter or two of air, it's gonna go through a centimeter of rubber, no problem. And he's like, oh yeah, you're right, I forgot. So 3 physicists have shocked themselves in the same institution. So it goes to show you that, you know, as much as we know what we're doing, we hurt ourselves too playing with the physics. Anyway, so enough of the Tesla coil. Oop, what's going on? It jumped. Wow, it really jumped. Okay, so enough of the Tesla coil for a second. The opposite can also happen. So a Tesla coil is an example of a step-up transformer. You take a wall voltage of something safe, like 120 volts, and you have a very small number of turns in the primary, and the secondary coil is not electrically connected to anything. Not electrically. It's just a second coil that is in close proximity to the first coil. Not electrically connected. And it feels the flux of the primary coil, but because of the loop ratio is so large, thousands and thousands of turns in the secondary, you can actually take that 120 volts, step it up to thousands of volts, maybe even 100,000 volts, and then that's how you get lightning. That's how you build up enough voltage to hit the breakdown voltage of air, and then you get lightning. So that's how a Tesla coil works. We needed this entire class to really hit this moment. Now, the opposite is true. You can have a step-down transformer. I've already explained that electricity through power lines is a very high voltage, and I'm sure you've heard that. You maybe even see signs on like posts and things, danger high voltage. However, we don't have 24,000 volts coming into our wall outlets. We only have 120 volts. How does that happen? Well, the reverse is true. If you want to solve for the secondary, like we've done, let me zoom out a little bit, like we've done here. If the primary equals, I don't know, like a few thousand, and the secondary equals, you know, like 10 or fewer or something like that, then the loop ratio is actually far less than 1. So you can actually convert this very high voltage, this 24,000 volts from the power lines, down to something safe. And you can manipulate it as whatever you want according to the loop ratio. And you may recall seeing these green boxes in and around your neighborhood. This, and maybe you played on them when you were a kid, because I used to when I was a kid, and your parents always, my mom used to yell at me, "Mark, don't play on that, that's dangerous." And my dad's like, yeah, whatever. My dad's a physicist, so he knew what was what. This is a transformer, and this is the transformer that actually steps down the voltage between the power line, the 24,000 volts, and the 120 volts. And you might be thinking to yourself, "Oh, I'm never touching that again." You know, you've got 24,000 volts traveling through that. And in fact, you might even hear the hum. If you walk near a green box, you might hear the hum, because it's such a high voltage. You will probably hear that hum. Anyway, the reason why it's safe, and you know it's safe because it's just, there's no fence around it. You know, people can climb all over it. So clearly, people who know what they're doing know that it's safe to touch and climb on and stuff like that. Otherwise, they would bury them or something like that. The reason why they're safe is they are enclosed by metal. That green stuff is metal, and that's not by accident. They did that on purpose. It's a Faraday cage. It's just a reverse Faraday cage, you know. Instead of being in it, we're sort of in it from the outside. So if there was ever a short circuit or something like that, the metal would provide the path of least resistance back to the ground and not somebody touching it. You know, your body is conductive, but it is far less conductive than metal. So it is safe to climb on, it is safe to touch, because, you know, if there was ever anything broken inside or a loose wire inside, you would just be funneling electricity into the ground and not into you. Okay. Here I have a short video for you that hopefully explains transformers, exactly what I've just explained, but it explains it with an animation and with a different narrative. So I'm hoping that we can take a bit of a pause here and you can watch the video, and hopefully it allows this to sort of sink in using an animation and a different explanation. So hope you enjoy the video.
A transformer is used to increase or decrease the voltage of an electrical supply. It's essential for transmitting electricity from a power station to your home, but it's also essential for using your mobile charger to adapt the 230 volt electricity from your main supply to the 5 volts needed to charge your mobile phone. In this video, I'm going to be looking at two aspects of transformers. First of all, explaining how they work, and secondly, showing you how to use the transformer equation. Physically, this is all a transformer is. On one side, you have a primary coil, that's wire that comes in, wrapped around and comes back out again. And on the other side, you have the secondary coil coming in, wrapped around, and back out. On the primary coil, you would attach your supply of power, whether that's the power station or your main supply. And on the secondary coil, you'd attach whatever your load is. So that could be a mobile phone, or it could be something much bigger, some lights, or an entire building perhaps. In between, we have an iron core here. Now, what's really important to remember is that there is absolutely no current flowing through this iron core. The electricity is kept within the coils and nothing flows between them. Firstly, let's think back to when you studied electromagnets. If you run a current through a wire, through any wire, it sets up a very weak magnetic field around the outside of that wire. Now, if you wind that wire up into a coil, what that will do is it will squash together all of those magnetic field lines to create something like this. This becomes a magnet with a north pole here and a south pole here. To create an even better electromagnet, we just need to put an iron nail through the middle of that coil, and it will become a much stronger electromagnet. This is almost exactly how the primary side of a transformer works. The current in the primary coil flows around here. That makes the iron core into an electromagnet. Now there's just one difference. Instead of using direct current that would flow continuously through our primary coil here, in a transformer you always have to use alternating current. The difference being that in alternating current, the electric current shuffles backwards and forwards 50 times every second in the coil instead of just flowing in one direction. Now this is really important because instead of creating an electromagnet with a north up here and a south up here, instead the north and south will switch around 50 times every second. So what was north will become south up here and north down here, and vice versa. 50 times a second, north and south will switch direction. Now, to understand how the secondary side of the transformer works, we need to think about how electrical generators work. When you move a coil of wire in a magnetic field, you will induce electricity in that coil of wire. That's how a generator works. Now, the clever bit about transformers is, even though there's nothing physically moving, the core and the coils are completely stationary, the magnetic field that is in this core, or around this core, is switching direction 50 times every second. So as far as the secondary coil here is concerned, it is seeing a moving magnetic field, and so an electrical voltage will be induced in the secondary coil. The more wires we wind around this secondary coil, the bigger that induced voltage is going to be. That's where our transformer equation comes in, and we'll come to that in a moment. But you can see here the primary coil has fewer windings than the secondary coil. This means that the voltage will be increased by this transformer. Time for a quick summary then. We have 4 steps to success. First of all, an alternating current flows through the primary coil, and this creates a magnetic field around the iron core. But that magnetic field is constantly changing direction because that electric current is alternating. Number 3, the movement of the magnetic field induces a voltage in the secondary coil. That's working just like a generator. And number 4, the more turns of wire we have in that secondary coil, the bigger that induced voltage will be. So that gives us control over whether the transformer increases or decreases the voltage. Here is our transformer equation. All it tells us is that the ratio between the voltages on the primary and the secondary coils is equal to the ratio between the number of turns in the primary coil and the number of turns in the secondary coil. For example, if we had a primary voltage of 230 volts, that's the mains electrical voltage in the UK, and a secondary voltage of 23 volts, that would tell us that the ratio between the two needs to be 230 divided by 23, or 10. Now if we have 1000 turns on our primary coil, we need to choose a secondary coil that has enough turns to make the same ratio. So we want a ratio of 10, so a secondary coil with 100 turns should be right. Let's check that. So 230 divided by 23 will give us 10, and 1000 divided by 100 would give us 10.
Okay, my keyboard and tablet froze halfway through that. Hopefully it was still recording and things, but I had no ability to turn on my camera, so I had to reattach my keyboard and stuff. Anyway, that aside, so I hope that was helpful and informative. It pretty much re-explained everything we just talked about, just using an animation and you know, a different person explaining. So anyway, let me take the keyboard back off, because I think I figured out with the Windows machine a way to get it unfrozen is to reattach the keyboard. Don't know why. Someone tell Bill Gates the problem. Anyway, moving on. So this brings us to the last sort of subchapter in transformers, we're talking about mutual, oh, what's going on? Okay, we're talking about mutual inductance and self-inductance. That's kind of like the last little chapter. So mutual inductance is a way in which, like, we can just quantify the phenomenon we just talked about. Okay, in a transformer, a properly designed transformer, we know that that flux transmission is perfect, right? The flux felt by the primary coil is exactly the same as the flux felt by the secondary coil. That's by design. What if we just happen to have two coils that were near each other? Well, then that transmittance of flux will be non-zero, but not perfect. This is what we call mutual inductance, is the act of inducing a voltage in a second coil. And there is a coupling coefficient called M. M is the mutual inductance coefficient. And M can range, you know, it can be small, you know, if the coil is really far away and it's an air gap and there's no iron core to like really funnel a magnetic field, then the coupling coefficient, M, the mutual inductance coefficient, M, will be quite small because, you know, there's nothing helping it. So something like this, for instance, there's no iron core. You see here that some of the field lines are missing the coil. So it's not a perfect transmission. It's an imperfect transmission. So if we're talking about a transformer and there's an equality there, the equation is super easy, right? Because there's an equality, we can just get the transformer equation. If there is not an equality there, then it becomes hand-wavy. Then it becomes, well, look, we have to come up with a number, M, that quantifies the ability the two coils have to quote unquote talk to each other, feel each other's presence. That's called M. So we say, okay, the voltage from the secondary is Faraday's law. So Faraday's law says the voltage in the secondary is going to be the changing flux in the secondary. And the changing flux in the secondary is going to be the number of turns in the secondary times the flux through one of the loops in the secondary. And this is where you swap out this, because you don't know this. This is really, come on. Oh, now I'm not drawing. Come on. Okay, here. This is really the quantity we don't know when we have imperfect transmission. So we have to swap that out because that's not something we can measure. And as the video described, that secondary coil is not in any way electrically connected to the first one. So we really have to fudge it. So what we're doing is we're saying, okay, this is going to be some function of the changing current in the primary coil. And what is that a factor of? I mean, well, it's a factor of distance, it's a factor of orientation. You know, you could have 5 amps in the primary coil, but if the secondary coil is really far away, then that 5 amps is going to be useless. So it's definitely a function of the current in the primary coil, but all of the other factors that we just don't know how to put into a variable, that's M. So this is sort of our fudge factor. What I'm saying here is there is no formula for M. There is no way in advance to calculate what M would be. M is something you have to measure empirically in the lab for that specific setup, for those specific coils in that specific orientation. Okay, it is not something that has a formula. You have to just set up your specific coils with your specific orientation, with your specific experiment, and then specifically measure what the M value would be for that specific. And that's the only way, the only way to account for all of the many possible imperfect transmissions of flux between these two coils. So That's all mutual inductance is. It's imperfect transmission. It's a transformer that isn't perfect. That's mutual inductance, a transformer that isn't perfect. Now, a common way in which we can do this is you can place the primary coil inside or around the secondary coil. So in this example here, they're not inside, they're just next to each other, right? They're side by side. One common way they can do this, and this is what a Tesla coil does, is they nest the two of them together. They have the primary coil here that generates, well, that has the current and generates the B field. And what they do is they take the secondary coil and they actually place it inside. So they usually wrap it smaller, and then that way they can nest it like Russian nesting dolls inside of the primary coil. And that makes it lighter. You don't necessarily have to use the iron core, and it maximizes the M value because they're lined up, they're as close as they possibly can, and all the variables are as optimized as humanly possible. Okay. I have a video for you that, now, by the way, Tesla coil it does use mutual induction. It is a transformer. It is an example of a step-up transformer, but it doesn't use an iron core. Now, because a Tesla coil does nest these two together, the transmission is nearly perfect. So often when we analyze a Tesla coil, we do use the transformer equation, even though it's not perfect because of that sort of nesting. But technically, because they don't have the iron core connecting the two of them, we really should be using the mutual inductance. But when we calculate it, it comes out pretty close to the transformer equation. So the grand finale of Tesla coils, I am so happy that there's a movie that has a very beautiful scene with Tesla coils. I have it here for you. Actually, I don't know why it didn't pop up. Hold on. I need the keyboard again for this. I don't know why it didn't pop up in here. Usually it does. But again, Windows, you can't always trust it to do what you want. There we go. So there's a scene from a movie, The Sorcerer's Apprentice, with Nicolas Cage and Jay Baruchel, I think his name is. And I actually loved this movie, quite frankly. I thought it was an amazing movie. It got really crappy ratings online, but I loved the movie. Maybe because of it was this nerdy physicist that becomes a sorcerer, which I think is just every physicist's dream, to be completely honest with you. There's a scene in the movie here that it shows him working in a lab for 2 years on building these Tesla coils, and by changing how much current and the frequency of this current, of this AC current, that goes into the primary coil of the Tesla coil, you can continuously change the voltage in the secondary coil, and then when it produces a spark or a lightning bolt, you can change the frequency of the current in the lightning bolt, which gives it a different pitch. If you have a 60 cycle AC, it'll sound a certain way. If you have a 50 cycle AC current, it'll give off a slightly different pitch of hum. If you remember sound is from 136, it relates to the frequency of the sound, and the frequency of the sound in a lightning bolt is proportional or a function of the frequency of the current going in. So the Tesla coil we have at UTM, it sings. It's a singing Tesla coil. We can change the attributes of the current going into the primary to manipulate the attributes of the current in the secondary to change the pitch of the lightning, and you can actually get a song. And I know there's a lot of special effects in movies. I'm willing to bet money that this is not a special effect. I'm willing to bet money, because Tesla coils are so easy to make, so easy. I'm willing to bet money they just did this. And the noises that you hear, other than the dubbing of the music over top, but the music from the Tesla coil is actually indicative, very close to what it actually sounds like in person at UTM when I do this demonstration. So I hope you enjoy this little bit of a snippet from the movie. Okay, well, that was unfortunate. I don't know why it's unavailable. Hold on, let me just take you to the YouTube.
Okay, enough with the studying. There's something I want to show you.
What are these things?
Tesla coils. I was using them to generate something called plasma. The thing is, I got so fixated on the technical aspects of it that I almost didn't notice something kind of beautiful. I think you'd better step into my cage.
Okay, it's definitely the first time anyone has said that to me.
I'm not surprised. Just hold on to this bar, please. Both hands. Yep. Okay. Okay. Hold on tight and enjoy the show.
Is it possible?
The coils are firing at such a high frequency that the sparks literally create sound waves as they fly through the air, which is nerdy.
You were listening. I played this song the other night.
These coils are my life. 2 years I'm down here working with them, and they're making their own music, and it was lost on me. I was never able to appreciate it until I met you. I heard you talking about music on your radio show, and I'm sappy.
Tell me what you want. Something that will light the roses. Sick of all the insincere. I'm gonna give all my secrets away. This time.
Okay, so I hope you enjoyed that. It was a little bit of movie magic, and definitely very romantic and a movie moment. And I think every physicist would absolutely love to woo a partner based on their physics abilities. That's just how nerdy we are, I guess. I don't know. But what I will say is I'm pretty sure it wouldn't be cost effective for the movie people to animate that. Tesla coils are very easy to make. Like very, very easy to make. And I mean, we have a musical Tesla coil at school. We've hooked it up to a piano. I play the piano, and I've played songs on our piano at school before with the Tesla coil. And the lightning sounds very similar to what we just heard. So, if we can do it for a couple $100 at UTM, I'm pretty sure the people who made this movie, I think that was real. I don't think that was animated, which is really cool. Now, obviously, toward the end of that clip, they dubbed in the actual song that they were trying to play over top. That is obviously movie magic, but before that is actually real. And one thing I will say is I can't remember if I've mentioned this before, but like I also play the saxophone, the piano, and my partner Julia, she plays the piano way better than I do. So, it's often the case that scientists have a very deep appreciation for music. And that's not uncommon because there's so much science in music. And, there's an element of romance to it as well, I suppose. But, as a physicist, I don't know, I just have this very, very deep appreciation of music, because not only do I know what music is, and, lightning is music, it's just a different instrument. You could actually play lightning like you could play the piano. But it's just, there's so many different elements to music and sound and the emotions that they sort of induce, and just sort of understanding every step of the process, the physics behind it and the biology of it, and how an ear works. It's just, I just find that humbling to no end. I just find that humbling. Okay, so the last thing is self-inductance. I don't want to dwell on self-inductance too much. That was a shitty segue. It was a very sappy moment, and I just shifted right back into course material.
I think I have a video of our Tesla coil. Do you want me to send it your way so you can share it?
Sure.
All right.
You mean like in the chat?
Yeah, let me see if I can find it.
Yeah, man. Was this on YouTube? Where did you find this? What's this video of?
It's like our Tesla coil at UTM that I just had on my phone.
Oh, on your phone. Oh, so you're sending me the actual video file.
Yeah, if I can find it.
Oh, okay. Well, I mean, you send it to me. Maybe I'll show them on Tuesday because we only have
cool.
10 minutes left. But yeah, no, if you can send it, then that'd be awesome.
Sure.
Okay. Anyway, sappy segue aside, because I'm terrible with segues. The very, very, very last thing I want to acknowledge in this chapter is that not only does the changing magnetic field in the secondary coil induce Faraday's law and induce a voltage, but the changing magnetic field that the primary coil feels, there's still Faraday's law in itself as well, right? Because you can't forget that the primary coil has a current through it and is thus generating a magnetic field through its own core, through its own center. And if the current is AC and constantly flipping back and forth, then a moment in time later, maybe we'll do green, a moment in time later, the B field will be going backwards, and the primary coil itself will feel a change in flux. So there is an induced voltage in the primary coil as well, and this is going to be sort of a back EMF in the primary coil, and we can quantify that back EMF again using a new parameter called self-inductance, you know, for that. Well, I guess there is an L in self, but I don't know why they didn't call it S for self-inductance, but I don't know. If I was in charge of naming conventions, I would have retired by now. Let's put it that way. So we'll just use whatever convention they use. So they use capital L, just like angular momentum was capital L. So again, I don't really know the logic behind where the capital L came from in this case, but anyway, capital L, it's a function of geometry, core material. Is it an air filled coil? Did you put iron in the center of it? Stuff like that. So we won't do very many problems with self-inductance and mutual inductance. I don't believe so. I just want you to know the concept. The concept is that Faraday's law is Faraday's law. And you know, any coil in any capacity that has a changing flux is going to experience a back EMF. So you can take advantage of that back EMF and induce a current in a secondary coil that is not electrically connected to anything. And a lot of what we have in day-to-day lives use this, but also it comes at a price. There's a back EMF in the primary coil that you have to battle with as well. One thing I will say though, with mutual inductance, this is how wireless chargers work. And you know, with the iPhone now and a lot of the Android phones, there's wireless charging, and your watches, a lot of the smart watches have wireless charging as well. You know, there's a primary coil in the charger, there's a coil somewhere in your phone, and that's how it charges, is with mutual inductance. And tap cards, with your credit card, when you tap, tap, tap on a machine, that's how the tap card works, there's mutual inductance there. There's some sort of changing current in the primary coil in the tapping machine, and it induces a small current in the computer chip, or I guess not a computer chip, but in the chip in the credit card, and that current in the credit card induces its own magnetic field and is able to transmit information to the circuit wirelessly, and then the credit card information can be then conveyed through a tap. So that's all really cool, and that's all a function of Faraday's law. So like Faraday's law is really, really important and really prevalent in everyday life. So that's why we saved Faraday's law to the very end, because we wanted to go out with a bang. Okay, so there's 5 minutes left. We did not get a chance to go through or to start geometric optics. I know in the schedule we were supposed to start geometric optics today, so it looks like we are about 1 chapter behind. And I know some of the pre-class questions involved optics today. I sort of took a little bit longer on transformers just because they're my personal favorite. Tesla coils are amazing. So it's okay, we're about 1 lecture behind, but as I said, with 136 we had like 14 chapters to get through, and 137 we only have 9. So when it's when we hit a fun part or a challenging part, I think it's good to slow down and sort of just really smell the roses and enjoy. So we'll resume a new topic on Tuesday, and we'll do geometric optics, or start geometric optics on Tuesday. A few announcements at the end. So you have, I believe, and please yell at me if I'm wrong when I say this, I believe we have our second midterm coming up next Friday. So like 8 days from now, I believe. And as the schedule indicates, that midterm is going to be strictly on magneto-blank. So that would be like magnetostatics and magnetodynamics. So Gauss's law for magnetism, Faraday's law, and Ampere's law. So magneto-blank, anything that involves a B field, bam, that's what's on this test. Now, perspective, I'll try to give you some perspective. The first test, I think went very well. You know, it was historically very, very average. The average, I think, was around a 52.5, somewhere between 52 and 53. And the distribution of marks looked pretty Gaussian. It looked like a normal distribution. So both of those signs together pointed to a well-balanced test, and the average is exactly where you would expect an average to be with a large sample size. So I think the first test went pretty well. You know, you could conceivably get an average of 50 if you have like half the kids or half the students up in the 90s, and then half the students down in the you know, down in the 10s or whatever. That would indicate a problem, right? That would indicate that there's something wrong with the test if there's a huge separation of marks like that. But the distribution of marks looks reasonably Gaussian. So I think the first test was fine, but I want to point out though that the first test only really involved one of Maxwell's equations, right? It was Gauss's law. And yeah, there were other concepts that compounded onto that. There was Gauss's law. Then we piled on energy on top of that. So Q delta V, we piled voltage on top of that. And then we piled current and Kirchhoff's laws on top of that. So yeah, I mean, I suppose that there was more than just Gauss's law, but overall though, there's four main equations in electromagnetism. It's the four Maxwell's equations, and the first test only involved Gauss's law. This test is going to have three of Maxwell's equations: Gauss's law for magnetism, Ampere's law, and Faraday's law. And even in the past two lectures actually past three lectures since Tuesday, you've seen how prevalent Faraday's law is, how many applications it has, how many facets it has, how many implications and concepts there are around it. For such a simple equation, you know, d phi by dt, it has so many different uses and avenues to think about. So please don't take this upcoming test lightly. It will be harder, it will be more difficult because the course has progressed. We have covered more material. And I just want to kind of remind you how the difference in amount of material on test one versus test two. Test one had one of Maxwell's equations, test two has three of Maxwell's equations. So I just want to make sure you're well prepared and you're well informed, and the expectation of kind of what's about to come is very clear for everyone listening. So I can't help people who don't listen and don't come to lecture, but for those of you who are here, I'm just trying to remind you, please be aware that there are three Maxwell's equations on this upcoming test. Okay, it's about 11 o'clock, guys, so I'm going to stop the recording now, and I will see everyone on Tuesday, and I'll hang back for a few minutes and take any outstanding questions. Okay, ciao for now.